Welcome back to Neural Intel. Today, we're diving straight into something pretty specific, but really interesting.
We are. It's at that intersection of AI and, well, hardcore hardware design.
Exactly. We're looking at customizing large language models, LLMs, for designing high-performance microprocessors, and specifically using VHDL.
Yeah, focusing on some technical work coming out of IBM, looking at how they're applying, cutting-edge AI to the nitty-gritty of chip design.
And our focus today, as always, is squarely on the technical side. The methods, the evaluations, the result. We want to really unpack how they did it.
Right. And for anyone wanting to follow up, the research papers are linked on our webpage in the bio. Definitely check those out for the full details.
Okay, so let's jump in. Why even try using LLMs for something like microprocessor design with VHDL?
Yeah.
What's the big motivation?
Well, the core driver is just the sheer escalating complexity of modern chips.
Getting harder and harder, right?
Absolutely. The demand for more power, for AI-specific optimizations on silicon, it keeps growing. And that means massive engineering effort.
And really specialized knowledge needed too, I imagine, especially for these complex architectures and the fast development cycles.
Precisely. And you mentioned VHDL. It's interesting because a lot of the LLM work in hardware seems focused on Verilog.
Yeah, why is VHDL still so important here, particularly for microprocessors, but also, say, aerospace or automotive?
That's a great point. VHDL is still really crucial in those areas. A big reason is its strong type checking.
Ah, okay. Like a really strict grammar checker for the hardware design itself.
Kind of, yeah. It helps catch errors much, much earlier in the process, saves a ton of time and, frankly, money. Plus, it's excellent at modeling concurrency, all those parallel things happening inside a chip.
Okay, so it's got inherent strengths that keep it relevant, even if Verilog gets more LLM attention generally.
Exactly, especially in these critical, high-reliability sectors.
So the motivation is clear, tackle complexity, and VHDL is key. But what were the specific sort of roadblocks or challenges the IBM team hit when trying to apply LLMs here?
Well, there were several big ones. First and foremost, security.
Right. Chip designs, that's serious intellectual property. Highly confidential.
Extremely. So you can't just train these models anywhere. It all has to happen in a super secure environment. Very different from a lot of typical AI development, which can be more open.
So they couldn't use public code repositories. It had to be internal protected data. The paper mentions a secure VPC in IBM Cloud.
Yes, Figure 1 shows it well. They set up the secure virtual private cloud. Inside that, they had separate isolated clusters for different stages.
Clusters for what specifically?
For pre-processing the data for the actual model training, and then for inference, when the model generates explanations or code.
And the data itself, how is that handled securely?
It was moved into multi-region object storage, also within the secure setup. And importantly, that storage had its own key protection. Everything communicated through the secure shared storage. It's a very deliberate lockdown architecture.
Makes total sense. You can't risk that kind of IP leaking. Okay, security is number one. What else?
The next major hurdle was just finding and structuring the knowledge.
Finding it. You mean it wasn't all neatly documented?
Not even close. Imagine decades of microprocessor design work. You've got knowledge scattered across specifications, design documents, maybe engineers' notes, insights people gained over years.
Wow, okay, so unstructured internal data everywhere.
Exactly.
Yeah.
Pulling all that together and getting it into a format an LLM can actually learn from, that's a massive job in itself.
How did they even start tackling that? Sound like finding needles in haystacks.
They really leaned on their subject matter experts, the SMEs.
The engineers with the deep design knowledge.
Right. Those experts were key in just identifying which internal data sources were actually valuable, separating the signal from the noise, filtering things.
Okay, so the SMEs guide the data collection, but then you need to label data, right, for the LLM to learn properly.
You do. And that brings us to the third challenge. There just aren't that many of these SMEs.
The expert bottleneck.
Precisely. These are highly skilled people. You can't have them spending all their time manually labeling data or constantly verifying model outputs. They need to be designing chips.
So, recap. High security needs, messy unstructured data, and not enough expert time. That's a tough set of constraints. How did they build their solution around that?
Their core approach was to customize a base LLM. In this case, they used an IBM Granite Foundation model.
Customize it specifically for VHDL and design explanations.
Exactly, and they used a couple of key techniques. The first was something called extended pretraining, or EPT.
Okay, extended pre-training. Let's unpack that. What does that mean here?
So they took the base Granite model, which already knows a lot about code and language generally, and they kept training it, but focused specifically on their internal, high-quality VHDL data.
The data curated by the SMEs.
Right. Both VHDL code snippets and related technical documents, giving the model a deep dive into the specific domain it needed to understand.
Like an immersion course in VHDL design. The paper mentions replay tokens to avoid catastrophic forgetting. What's that about?
Yeah, that's important. When you keep training a model on new specialized stuff, it can sometimes forget what it learned originally.
Was its general knowledge.
Kind of, yeah. So replay tokens are basically small bits of the original, broader training data mixed back in during this extended pre-training phase. It helps the model hang on to its general smarts while it's learning the VHDL specifics.
Clever, like reminding it of the basics while it learns advanced topics. Table A shows the token mix, right? Lots of VHDL, but also other code and docs.
Correct. About 162 million VHDL code tokens, 168 million other code, 14.6 million documents. And they did this EPT using powerful NVIDIA H100 GPUs in that secure cluster we talked about.
Got it. So that's EPT. What came next?
After EPT, they did instruction tuning, or IT.
Instruction tuning. Making it follow commands better.
Essentially, yes. They fine-tuned the EPT model on a dataset specifically designed to make it better at following natural language instructions, like explain this piece of VHDL code.
So EPT gives it the knowledge. IT teaches it how to use that knowledge in response to a prompt. Makes sense. They used A100 GPUs for that part.
That's right. Slightly different hardware, still within the secure setup.
Okay, logical steps. The paper also mentions this thing called model merging using SLRABI. Sounds a bit experimental.
It was. Model merging is a technique they tried, kind of as a potential shortcut. Instruction tuning takes a lot of compute resources.
Right.
So they experimented with taking the weights, the learned parameters from their EPT model, and mathematically blending them with the weights of a different base model that had already been instruction tuned.
Blending two models together, how does that work?
Using a technique called spherical linear interpolation, or SLRP. Because both models started from the same underlying Granite architecture, you can sort of interpolate between their learned states. The idea was to get an instruction-following model more efficiently without doing the full IT process on the EPT model.
Interesting. A faster route to a usable model, maybe? So they've built these models using EPT, IT, maybe merging. How did they figure out if they were any good? What was the evaluation process?
It was pretty rigorous, actually, multiple layers. First, they had the SMEs create very specific test sets.
Not just random code snippets.
No, carefully chosen examples representing the kind of real-world VHDL and design concepts relevant to their high-performance work.
The paper mentions two types of test sets.
Yep. One was for code explanation. So VHDL snippets paired with reference explanations written by the experts. Figure 2 shows an example.
Okay, and the other type?
Multiple choice questions. These tested the model's grasp of fundamental concepts, digital design, processor architecture, VHDL syntax itself. Figure 3 has a sample. And crucially, all these questions were reviewed by multiple experts for relevance and difficulty.
How many questions did they end up with?
They curated 80 code explanation examples and 263 multiple choice questions, a focused, high-quality test suite.
Okay, solid test sets. How did they use them to score the LLMs?
For the code explanation part, the first step was direct SME evaluation. The experts looked at the explanations the LLM generated for those 80 VHDL snippets.
And scored them somehow.
Yes, using a detailed 5-point Likert scale. They rated each explanation on correctness, completeness, how concise it was, and consistency. Figure 4 shows the platform they built to help the SMEs do this scoring efficiently.
That sounds thorough, but back to the bottleneck problem. Very time-consuming for those SMEs, right?
Exactly, which leads to probably the most innovative part of their evaluation work, the LLM-as-a-judge.
An AI judging another AI's work. Tell me more.
It's a fascinating approach. They basically trained other LLMs to automatically score the explanations coming from the main models they were testing. The goal was to reduce the reliance on manual SME scoring.
How did they get an LLM to act as a judge? What was the setup?
They used a specific prompting strategy, which is shown in Figure 5. They'd give the judge LLM the original VHDL code, the expert written reference explanation, and the explanation generated by the model being tested. Then the prompt would ask the judge LLM to score the tested model's explanation based on how well it matched the reference, using a defined scoring system. They tried 3 different LLM-as-judges.
And did the AI judges agree with the human experts?
Amazingly well, actually. They found really high correlations like 0.93 to 0.99 between the LLM judge scores and the human SME scores.
Wow, that's incredibly high. That really validates the approach, doesn't it?
It does. It suggests LLM as a judge is a viable and much more scalable way to evaluate these kinds of models. They even used a normalized score from one judge, Judge 2, for a lot of their later analysis.
That could really speed things up. What about generating the explanations themselves? Did they try optimizing that? The paper mentions beam search.
Right. So during inference for code explanation, instead of the model just picking the single most likely next word at each step.
Which is the default greedy approach.
Exactly. Beam search explores a few of the most probable sequences simultaneously. It keeps, say, the top 3 or top 5 best paths open as it generates the explanation.
Why do that?
It can potentially lead to a better overall explanation because it doesn't commit too early to a path that might seem good locally but isn't optimal globally. They tried beam widths up to 5 and checked the results using their LLM-as-a-judge scores.
Okay, so a really thorough approach to building and testing. What were the headline results? Did the customization actually work well?
Yes, the results were definitely positive. First off, the extended pre-training made a huge difference.
How big?
The SME scores for code explanation jumped from about 43% for the base model way up to 69% for their best EPT model. A really significant gain just from that domain-specific pre-training.
That clearly shows the value of feeding it relevant VHDL data. And the LLM-as-a-judge validation was key, too.
Absolutely. That strong alignment proved it was a reliable way to evaluate performance, which is crucial for faster development cycles.
What about instruction tuning and that merging technique? Did they add further value?
Instruction tuning pushed the performance up a bit more to an estimated 71% SME rating, and the model merging experiment, that also performed pretty well, hitting a 67% normalized score.
So merging could be a decent, cheaper alternative to full instruction tuning.
It looks promising, yeah. A more resource-efficient way to get good instruction-following capabilities.
They also looked at newer base models.
Right.
How did those fare?
That was really interesting. They tested some more recent powerful base LLMs on their VHDL explanation task without any custom EPT or IT. They scored much higher right out of the box, up to 85%, potentially even better with customization. It shows how quickly the underlying LLM tech is improving, especially in reasoning abilities, which helps even in specialized domains like this.
That's exciting. Progress in the base models lifts all boats, essentially. What about the multiple choice questions testing general knowledge?
The picture there was a bit different. Their custom EPT and IT on the original base model only gave small gains.
Really?
It seems like those general knowledge and reasoning capabilities tested by the multiple choice questions are more inherent to the base model architecture. The newer base models they tested did much better on the multiple choice questions, again suggesting their improved core reasoning. One hit 61% accuracy even before any VHDL training.
Interesting distinction. And did beam search help improve the explanation quality?
It showed potential, yes. Using beam search with widths of 2 or 5 pushed the normalized scores for code explanation up to 77%, compared to 71% with a beam width of 1. So exploring multiple options during generation can indeed yield better results.
Okay, so they've developed these models, proved they work, validated evaluation methods. What happens now? Are engineers actually using this?
They mentioned initial deployment, yeah. They've started rolling out the instruction-tuned model internally and, crucially, included a user feedback mechanism.
So engineers can rate the explanations they get.
Exactly. That real-world feedback is gold for figuring out where it works well and where it needs more work. Future plans involve more fine-tuning, especially on weak spots, adding more tasks the LLM can do, using those newer base models, and exploring more advanced AI techniques.
This has been a fascinating deep dive. Customizing LLMs for something as specific and technical as VHDL design really shows the practical power of AI in specialized fields.
It really does. The progress in the training methods, things like the LLM-as-a-judge for evaluation, and the performance they're getting, especially with newer models, it all points to AI becoming a really significant productivity booster for hardware engineers.
And I think the focus on security and leveraging that deep internal knowledge base highlights how these technologies can be applied effectively, even within large organizations with valuable IP. It's not just about open source data.
Absolutely. It shows a path for integrating AI into these complex, sensitive industrial workflows, tackling the unique challenges involved.
Well, hopefully this exploration has given you, our listeners, some valuable technical insights into AI and hardware design. What are your thoughts on how AI might change chip design? What challenges do you see?
We encourage you to check out those research papers linked on our webpage to learn even more.
Definitely. Keep exploring, keep learning, and join us next time on Neural Intel.